So we're now going to take a look at the CyclicSearchWithCyclicBarrier class. And this also, of course, indirectly extends TaskGang via search TaskGang common cyclic, which in turn extends search TaskGang common. So we've got a bit of an inheritance hierarchy going on here. And this will also showcase the Java CyclicBarrier synchronizer. So CyclicBarrier is another Java barrier synchronizer. You can see it's got a few more methods than Countdown Latch has. And what it does is it allows a fixed number of thread objects to wait for each other to reach a common barrier point during a multi-cycle search for words. One example of a human-known use of a cyclic barrier for cycles would be an assembly line where a fixed size group of workers coordinated each stage in the assembly line to build various parts of cars that are moving by in phases. So you might have one group of people who assemble the transmission, another group of people who might put in the seats, another group of people might put the upholstery or the cover on or the wheels on or the lights on or the electrical system or whatever. And each one of them would have fixed group. There might be 4 workers per station and they would take turns as the stuff went whizzing by. In the parlance of the cyclic barrier in Java, threads are referred to as parties. Not quite sure why they do this, but they don't call them threads, they call them parties. However, threads and parties are one and the same in the cyclic barrier context. There's also something else that's called an optional action that can be called when a barrier is tripped. In other words, after all the parties arrive, but before we go to the next cycle. This barrier action can do things. Typically, it is used to initialize the input for the next phase or the next cycle. Cyclic barriers are well suited for fixed-sized, cyclic, entry, and or exit barriers. So you can do all 3 things. You can do cyclic type of processing. You can do entry barriers. You can also do exit barriers. However, you need to make sure you have a fixed number of threads. The other thing you can do is you can have the barrier reset manually at any point. You can essentially throw an exception, which will break the barrier and then cause it to be reset. In contrast, Java's countdown latch that we looked at earlier does not enable the barrier to be reset. You can't reset it other than by throwing an exception, which is not the same thing. It doesn't reset anything. It just causes an exception. As you can see here, we're now going to talk about the cyclic search with cyclic barrier class implementation. And this is available at this link, and it uses a cyclic barrier to keep searching a fixed number of input strings using a fixed number of thread objects until there's no more input to process in the cycle. Now, what we're going to do here is we're going to customize the TaskGang framework to use a cyclic barrier, keep going until the input is done. And the number of input string objects to process for each cycle must be identical. We can't have 4 input strings in one cycle and 6 on the next, and then 3 on following, and so on. They have to always be the same number, because the threads and the input elements are all bound together inexorably. So that, of course, requires us to initialize the cyclic barrier, and we do that with our initiate hook. And you can see what we do is we make ourselves a new cyclic barrier of a given size, and then the barrier action, which is what you can see here as this lambda expression, is going to get the next input. And if there is no more input, we're done. Otherwise, we will go on to the next cycle. So in this case, the cyclic barrier will have a parties count that corresponds to each element in the input list and this barrier action that gets the next list of input data when it's triggered. In other words, when all the items have shown up and before we go to the next phase. The task done method, as you can see here, uses the cyclic barrier that we created, this mCyclic barrier field, to wait for all the threads to finish each cycle. So the await call here will be called by all the threads, and no thread can make forward progress until they're all calling await, so they all have reached that particular point. And then we use the exit barrier that is defined as part of the search TaskGang common cyclic superclass in order to count down if there's nothing left, if all the input is done, and then have the main thread await when it has a chance to continue because all the threads are done processing the cyclic information. Once again, each thread runs the same logic of processing the input. This is not changing. It's all pretty much the same. So let's go ahead and take a look at the code. So here's the cyclic search with cyclic barrier implementation. As you can see, it defines a cyclic barrier, and that's what it's going to use to coordinate the interaction of all the threads that it spawns, all of which will be virtual threads, of course. Its constructor simply calls up to the superclass, which in this case is search TaskGang common cyclic, and it passes in the words define and the strings to search. In turn, that will call up to its superclass, where it'll finally get initialized in search TaskGang common in its constructor, which will store these values values in the proper fields. Here's the initiate hook. This is pretty cool. We make ourselves a new cyclic barrier of size, which is the number of parties. And we then have the barrier action, which is going to try to get the next input to process. And if there is the input, in other words, if the input is not null, then we have work to do. We're going to start the next cycle. We print the cycle and say how many threads that we've got. Otherwise, we're done. And once we set up this new cyclic barrier, we say that we're starting the cycle and we indicate what cycle we're on. Here's the task done method. As you can see, task done gets called back by the framework after process input returns successfully. And what task done is going to do for every virtual thread that's called is going to simply call the await method on the cyclic barrier field, which we defined up here. And that's going to go ahead and block that virtual thread until all the other virtual threads reach that same point. And then at that point, it will go ahead and continue on to the next phase in the cycle if there is any more input left. As you can see here, we're using CyclicBarrier as an exit barrier. So it's used to coordinate the exiting of a cycle and the beginning of the next. So I guess technically speaking, it's used both as an exit barrier for the previous cycle and the entry barrier to the next cycle. So that's the end of our walkthrough of the Cyclic Search with CyclicBarrier class in the Barrier Task Gang program.